Welcome to the lecture series on CFD, Part 2. This is lecture 39 on simulation of flows with phase change. This lecture begins with an introduction to phase change modeling, followed by a deeper look into phase change at liquid-gas interfaces. The next topic is the modeling of phase change when the liquid-gas interface is resolved by the computational grid. Two examples are described in more detail: direct numerical simulation of bubble growth in a superheated liquid, and largely simulation of flow and phase change in a pool boiling experiment simulating departure from nucleate boiling. When the computational grid does not resolve the liquid-gas interfaces, simulation of phase change relies heavily on empirical models, which are usually specific to particular geometries or operation parameters. Only a brief description of possible approaches is given. Simulation of flows with cavitation is covered in more detail. One of the most widely used cavitation models, which is available in all commercial codes, Schnerr-Sauer model, is described. The example of prediction of tip vortex cavitation on a propeller is used to highlight the interaction of discretization and modeling errors and the importance of local grid refinement to capture critical flow features. Phase change in fluid flows is closely related to heat and mass transfer by molecular diffusion and convection. Numerical analysis of heat and mass transfer is done at one of these two levels: research for improving our understanding of physics, or solving engineering problems using available software tools. Engineering problems are usually too complex for accurate analysis approaches like direct numerical simulations or large eddy simulation. They often need empirical input and use runs equations. Detailed, accurate analysis is usually limited to a small fraction of the real problem, with the aim to provide valuable insight, deliver data that cannot be measured, and provide correlations for simpler methods. At a solid fluid or gas-liquid interface, heat is exchanged solely by conduction. Convection and turbulence only affect the temperature gradient at the interface. This figure shows a temperature profile in fluid near a wall. The tangent to this profile at the wall represents the temperature gradient which, when multiplied by the heat conductivity in fluid at the wall temperature, defines the heat flux between fluid and wall. If the grid resolves the boundary layer near the interface, then the heat flux can be exactly computed using this expression. When the grid is not fine enough to resolve the gradient, wall functions are used. Heat flux is expressed as a function of wall temperature and the temperature at the near wall set center, assuming a logarithmic profile, for example the log law. See slides 9 to 17 in lecture 32b. The same approach is valid for mass transfer. The mass flux is equal to the product of diffusivity coefficient and the gradient of species concentration at the interface. We shall only consider phase change at the liquid-gas interfaces. Melting and solidification will not be covered. In fluids, phase change, that is evaporation or condensation, takes place at liquid-gas interfaces. Phase change can be driven by pressure difference, also called mechanically driven phase change, or by temperature difference, called thermally driven phase change. Examples of pressure-driven phase change are cavitation, which is caused by a low pressure in a cold fluid, and flashing, caused by suddenly reduced pressure in a hot liquid. There is no external heat supply or removal involved. Pressure in liquid is below saturation level for given temperature, as indicated by this figure, showing a growing cavitation bubble, and the heat required for the phase change is taken from the surrounding liquid, that is, it is cooled down. Cavitation usually takes place in a liquid flow, and the amount of liquid that evaporates is small relative to the flow rate, so the cooling down of liquid is usually negligible. Thermally driven phase change examples are boiling and condensation. The heat is externally supplied or removed, for example, by heating or cooling the walls. This figure shows a growing vapor bubble as an example of boiling. Temperature in liquid is above saturation level for given pressure. If a phase change takes place in a fluid flow, the conservation equations contain additional terms describing interfacial heat and mass transfer. If the interface is resolved and the finite volume grid is adapted to it, the additional terms are parts of cell-phase fluxes. If the grid is not adapted to the interface or the interface is not resolved, these terms need to be converted to specific volumetric terms. See surface tension terms in VOF method, slide 27 of lecture 35. For unresolved interfaces, the concept of interfacial area density is often used, representing the area of bubbles or droplets per unit volume of the continuous phase. The interfacial heat and mass transfer models are usually developed for a single bubble or droplet and then applied as volumetric source terms by multiplying them with the effective number of bubbles or droplets inside the control volume. The mass transfer rate due to phase change at a bubble or droplet surface can be expressed via the rate of change of bubble radius, which may vary over bubble surface, as indicated by this expression. It basically says that if the interface has moved by delta r over a time step delta t, the volume between the two positions multiplied by the liquid density is the mass of liquid that has evaporated. Temperature and pressure are often assumed to be constant inside bubble at T sat and P sat. To evaporate a unit mass of liquid at constant saturation temperature requires a supply of thermal energy, which is called the latent heat of vaporization. The heat transfer rate due to phase change can therefore be expressed via the latent heat L and the mass transfer rate as given by this expression. Heat is applied to the interface by conduction and convection from the surrounding liquid. At the interface, the heat is transferred by conduction alone. If we assume that the vapor temperature is equal to saturation temperature, that is Tv equal T sat, we can express the heat flux as the product of heat conductivity in liquid and the temperature gradient at the interface on liquid side as given by this expression. Using relations from preceding slide, the bubble growth rate can thus be expressed according to this expression. If the grid is fine enough to resolve the thin thermal boundary layer at the interface, both heat and mass transfer can be directly computed without using any additional models. This is done in direct numerical simulation, DNS, of phase change. Examples are shown in slides 11 and 12. In a more general situation, if the temperature of vapor inside bubble is not equal to the saturation temperature, the mass transfer rate is governed by the heat flux to the interface from both sides, as given by this expression. The computational grid is often not adapted to the phase change interface, but an interface capturing approach is used. If a simulation of boiling is conducted using the volume of fluid method described in lecture 35, the equation for volume fraction of vapor contains a source term QV, which describes the phase change per unit volume. For a single species phase change, the volumetric source term is derived from the heat flux to the interface, latent heat, and interfacial area density given by this expression. If the interface is sharply reconstructed, the interfacial area density can be computed as the interface area within the control volume divided by the cell volume. Here is an example of simulation of phase change with a resolved interface. Direct numerical simulation of bubble growth in a quiescent superheated liquid starting from an initial bubble radius of 50 micrometers has been performed by Buresh and Sato both in the absence of gravity force and under gravity conditions. For a detailed description, see the open access paper by the authors. Simulation started from an initial bubble radius of 50 micrometers. For this case, an analytical solution for bubble radius variation over time is available. The plot on the right shows that, with grid refinement, the results of DNS tend toward analytical solution with first-order convergence. The left figure shows an instantaneous plot of four variables: superheat, that is the difference between liquid temperature and saturation temperature, the volume fraction field, the pressure field, and mass source in the equation for liquid volume fraction. The interface is well resolved, as can be seen from the plot of volume fraction of water. Pressure inside bubble is higher than in the surrounding liquid because of the surface tension and large curvature, that is, small bubble radius. The mass source is active only in cells containing the liquid-gas interface. The thermal boundary layer around the bubble is well resolved, allowing for the computation of heat flux and thus the mass transfer rate as described in the preceding two slides. Because of the absence of gravity, the bubble is not moving and has a spherical shape. In the presence of gravity, the buoyancy causes bubble motion in the direction opposite to the gravity vector direction, and its shape changes. The pressure around the bubble is now non-uniform, with the lowest value where the highest relative velocity is obtained. Note an extremely high temperature gradient on the bubble front, and a much lower gradient at its back and in the wake. The mass source becomes negligible around the symmetry axis in the wake because the superheat near the interface is practically negligible. The growth of the predicted normalized bubble radius with time is in reasonable agreement with experimental data. For further details, see the open access paper by the authors. It is today possible to perform direct numerical simulation of flow, heat, and mass transfer around a moderate number of bubbles, 100 to 1000. Such simulations can be considered numerical experiments performed under well-controlled conditions. Data obtained from such DNS can be used to tune models employed in LES and RANS simulations. Although the heat and mass transfer at the interface are in DNS not affected by modeling errors, uncertainties arise from discretization errors, as seen in slide 11, and assumptions related to initial and boundary conditions, for example, nucleation sites, etc. In the next three slides, we present the results from LES of pool boiling over a wide range of regimes, from nucleate boiling to film boiling. Details can be found in the article by the authors of this study. This plot shows the solution domain. A cylindrical copper block is embedded in thermal insulation, and a constant heat flux is applied at the bottom. Above the two solids is liquid. The computational grid has 224 by 224 by 300, roughly 16 million cells, with a grid spacing in vertical direction of 125 micrometers. The time step delta t was between 3 and 0.5 microseconds. The heat flux applied at the bottom of the copper block varied between 50 and 1500 kilowatt per square meter. Energy equation is solved simultaneously in both solid and liquid regions, conjugate heat transfer analysis. Smogorinsky model with the constant CS set to 0.17 was used. The location of nucleation sites at which vapor bubbles begin to grow was prescribed using random numbers. The nucleation sites were activated when the copper surface temperature reaches the prescribed temperature, which was obtained from experimental results. The radius of bubble seeds was 125 micrometers. In this plot, the locations of nucleation sites with seed bubbles are shown, colored with the nucleation activation temperature according to this color table. The higher the temperature, the more nucleation sites become active. At the low heat flux of 100 kW per square meter applied at the bottom of the copper block, it takes about 1.5 seconds to obtain a nearly steady wall temperature at the interface to liquid of about 113.55 degrees Celsius. The heat flux at the interface oscillates around 100 kW per square meter because of growth and departure of vapor bubbles. A small number of nucleation sites are activated because of the low wall temperature. Water is superheated by about 5 degrees Celsius near the wall surface. Every time a bubble departs from the wall, cold liquid comes in contact with the wall, creating cold spots on the wall surface. With the increase in boundary heat flux, the temperatures in copper block increase. This leads to more nucleation sites at the interface to liquid becoming active and a faster growth of bubbles. Many bubbles coalesce to larger bubbles, which they form and also break up as they rise. At the highest boundary heat flux, we see events of large vapor clouds building up and departing. The temperature and the local heat flux are highly non-uniform at the solid-liquid interface due to frequent departure of bubbles from wall. At the boundary flux of 1500 kW per square meter, all nucleation sites are active. The temperature in the copper block increases, and after some time the whole solid-fluid interface is covered by a film of vapor. The boiling process transitions from nucleate boiling to film boiling, with evaporation taking place at the interface between vapor film and liquid. The evaporation rate reduces compared to the case of nucleate boiling, with many bubbles growing and departing, and with it also the heat transfer rate from solid to liquid. The heat transfer coefficient drops to about half of the value at the boundary heat flux of 1200 kW per square meter. The departure from nucleate boiling and the onset of film boiling is called burnout because with a constant heat supply and a halved heat transfer coefficient, the temperature of wall surface must increase to obtain the same heat flux that is externally supplied. This can result in wall overheating above the melting temperature, with catastrophic consequences if it happens in boilers or heat exchangers. This diagram shows the comparison of heat transfer coefficient obtained in experiments and in LES. The agreement is good, considering the spreading of experimental data. In most simulations of engineering flows, liquid-vapor interfaces are not resolved. Therefore, in both Euler-Lagrange and Euler-Euler types of simulations of multiphase flows, the interfacial heat and mass transfer is modeled. Heat and mass transfer coefficients are obtained from empirical or theoretical data correlations. Their validity is usually limited to a small class of flows, for example, boiling on a horizontal rod, boiling on a vertical rod, etc. Modeling errors can be significant. The models for heat and mass transfer in two-phase flow solvers make often the governing equation stiff and difficult to solve, especially when both phases are treated as Eulerian, that is, continuous. The simplest approach to the simulation of two-phase flows is the mixture model. In this case, only one set of conservation equations for the mixture is solved, plus the volume fraction equation for one phase. Such models are often used to simulate cavitating flows. The heat transfer is usually not considered because only a small amount of liquid evaporates and liquid temperature does not change significantly. Cavitation models assume the presence of seed bubbles in liquid, which can grow if the pressure falls below the saturation level for given temperature. Seed bubbles usually contain non-condensable gas, for example air. They are present either in the form of free bubbles or as gas pockets in crevices on particles. Pure, that is filtered and degassed liquid, can sustain high tensile stress, that is negative absolute pressure. This diagram shows the maximum measured tensile stress in water as a function of temperature. At room temperature, the purified water used in experiments could sustain the absolute pressure of minus 280 bar before onset of cavitation. However, liquids in daily use always contain impurities. This figure shows a small particle embedded in liquid containing a small gas pocket in one crevice. This interface between gas and liquid leads to the phase change as soon as the pressure in liquid drops below saturation pressure. Cavitation can be significantly influenced by filtering, that is, removing particles with potential cavitation seeds, and degassing, that is, removing non-condensable gases, both as free bubbles and dissolved in liquid. This reduces the number of cavitation seeds and can significantly postpone the onset of cavitation. The absolute pressure in cavitation bubbles is close to saturation pressure at given temperature, that is, it is always positive. However, the absolute pressure in the carrying liquid can be substantially negative. Most widely used cavitation models are based on an approach similar to volume of fluid method used to simulate flows with free surfaces, described in lecture 35. The only difference is that the transport equation for vapor volume fraction contains a source term which accounts for the phase change, that is, mass transfer. This source term is usually derived using the assumption of a homogeneous distribution of spherical vapor bubbles in liquid. The growth and collapse of bubbles is modeled using a version of the Rayleigh-Plesset or similar equation. On the left-hand side, we have the rate of change of bubble radius, also called interface velocity, and its time derivative, or interface acceleration. The first term on the right-hand side is the difference between saturation pressure and the pressure in liquid surrounding the vapor bubble divided by liquid density. The second term represents the pressure jump across the interface due to surface tension, delta P equal to sigma divided by R, with sigma being the surface tension coefficient. This effectively means that small bubbles start growing only when the local pressure drops below Ps minus delta P. The last term on the right-hand side describes the effects of liquid viscosity, which postpones bubble growth when dR by dt is greater than 0, but accelerates its collapse when dR by dt is smaller than 0. In many cases, the two frame terms in the equation shown in the preceding slide are dominant. For this reason, in most CFD codes, the simplified Rayleigh equation is used to describe the bubble growth rate as a function of pressure difference. This is a very crude approximation, taking the square root of the absolute value of pressure difference and assigning a sign to it. The growth and the collapse speed are thus assumed to be the same for the same pressure difference, which is not true. The liquid and the bubbles make a two-phase mixture and, in most cases, single bubbles cannot be resolved in a numerical simulation. The most widely used cavitation models involve two assumptions. Seed bubbles are uniformly distributed in liquid, as indicated by this figure, with N0 bubbles per unit volume of liquid, and all seed bubbles have the same initial radius. These assumptions introduce modeling errors and require tuning. The problem is that the liquid quality is often not known. Measurement-based data from literature indicates 10 to the power 8 to 10 to the power 14 seeds per cubic meter of seawater. Cavitation seeds are also present at rough walls, in crevices due to wall roughness, as indicated in this figure. The rough wall is not perfectly wet. This is especially true for walls which are not permanently submerged, like in fuel injection nozzles, where liquid fuel flows at a very high speed along the wall for a very short period of time. Gas pockets remain trapped in crevices and serve as seeds for cavitation in case of favorable pressure distribution. The conservation equation for vapor volume fraction is given in slide 10. The source term on the right-hand side describes the rate at which liquid evaporates or vapor condenses at the surface of bubbles. It can be obtained from the bubble growth rate. We just need to know how many bubbles are present in the control volume. We define two model parameters, number of seed bubbles per unit volume, N0, and the initial seed bubble radius, R0. This allows us to compute the number of bubbles within control volume, N, and the vapor volume for given bubble radius as given by these two expressions. Here Cl is volume fraction of liquid, V is the cell volume, and Vb is the volume of a single bubble. The volume fraction of vapor in control volume V is then equal to the product of the number of bubbles in the control volume and the volume of a single bubble divided by the cell volume. For a given vapor volume fraction, one can compute the bubble radius from the same equation as given by this expression. The growth rate of bubble volume, dr by dt, must be provided by another model. This can be achieved using methods described in slides 8, 9, 21 and 22, leading to the following expression for the source term. This nonlinear source term needs to be updated in each outer iteration within a time step. The volumetric source term is valid when the cavitation bubbles are smaller than the cell size and are not resolved. Many authors introduce a multiplier to the source term which is different for bubble growth, often greater than 1, and bubble collapse, often smaller than 1. The model described in slides 24 and 25 is called Schnerr-Sauer model. The convection term in the equation for vapor volume fraction does not require special treatment as when the VOF method is used to simulate free surface flows, because in most cases there is no sharp interface between vapor and liquid. The vapor volume fraction varies gradually. Let's have a look at an example of simulation of a cavitating flow. The figures below show the photograph of the Potsdam propeller test case and the arrangement from the experiment in a cavitation tunnel. Propeller diameter is 250 mm and shaft diameter is 50 mm. The tunnel cross-section is 600 mm by 600 mm with rounded corners, and the propeller rotates with 25 revolutions per second. The solution domain contains a single propeller blade with periodic conditions in circumferential direction, simulating an open water test in a cavitation tunnel. Computations were performed with SimCenter StarCCM Plus software using second-order discretization in space and time and Schnerr-Sauer cavitation model. Both runs and LES approaches were tested. Unstructured grids made of polyhedral control volumes with local refinement were used. The aim of the study was to predict tip and hub vortex cavitation. In the grid without local refinement within tip vortex, no cavitation within vortex was predicted. The location of the tip vortex could be visualized using vorticity isosurface shown in this plot. This isosurface was used to define the zone in which the grid needs to be locally refined. These three plots show a longitudinal section through grids with different levels of refinement within tip vortex, d over 400, d over 800, and d over 1600. Other than within tip vortex, the three grids are almost the same. The thrust and torque on propeller blade did not change much after the grid was successively refined, but the refinement had a significant effect on cavitation evolution. Without local grid refinement, the pressure minimum in the tip vortex core was severely underpredicted, which is why no cavitation there was predicted. Already at the first level of local refinement, the cavitation in the core of the tip vortex appeared. These two plots show the contours of pressure and axial velocity component in a longitudinal section along propeller axis, cutting across the tip vortex downstream of the blade. The white line across tip vortex indicates where the radial profiles shown in the next slide are taken. These plots are from the RANS simulation on the fine grid within tip vortex using leg EB K epsilon turbulence model. These two plots show profiles of pressure on the left and axial velocity component on the right across the cut through the tip vortex downstream of the blade, as indicated by a white line in the pressure contours plot, computed on three grids. With the first level of local refinement, the absolute pressure in the vortex core barely drops below saturation level, and the velocity minimum is not well pronounced. With further local refinement, the low pressure zone within vortex core becomes wider, and the velocity minimum becomes very narrow. Outside tip vortex core, the solution does not change much by the local grid refinement. The table shows the effects of the local grid refinement on thrust and torque. The effects are very small. The difference between values obtained on the grid with very fine grid within tip vortex and the grid with the first level of refinement, labeled fine and coarse respectively, is less than 0.2%. These results were obtained with RANS approach and the leg EB K epsilon turbulence model. These plots show isosurface of vapor volume fraction 0.05 computed on grid with coarse, medium, and fine grid within tip vortex using RANS approach and the leg EB K epsilon turbulence model. With the first level of tip vortex refinement, cavitation dies out too soon. Without local grid refinement, there was almost no cavitation within tip vortex. With each grid refinement, the tip vortex cavitation becomes stronger. Local grid refinement is essential to resolve extreme pressure and velocity gradients across tip vortex, as shown in the preceding slide. These plots show contours of turbulent viscosity ratio in a longitudinal section along propeller axis on the left, and isosurface of vapor volume fraction 0.05 on the right, as predicted with leg EB K epsilon model, upper plots, and LES with Weyl subgrid model, lower plot. On the grid with medium resolution of tip vortex, that is grid spacing of d over 800. RANS turbulence models overpredict turbulent viscosity within tip vortex, which results in reduced velocity gradients and higher pressure. This is why the cavitation inside the tip vortex core is weak and dies out soon in simulations based on Run's approach. With LES approach, turbulent viscosity is much lower within tip vortex. This is why steep velocity profiles across the vortex core are not smeared and a much lower pressure in vortex core is obtained than with Run's approach. Only with LES, the cavitation within tip vortex lasts downstream of propeller as long as the grid is fine enough. These plots show the isosurface of vapor volume fraction 0.05 computed on the fine base grid with a fine grid within tip vortex using LES approach on the left, and the photograph from experiment by SVA Potsdam on the right. In the simulation, tip vortex cavitation stops when the grid is coarsened downstream of propeller. The twisting structure of vapor zone is similar in simulation and in experiment. The result from LES agrees much better with experiment than the result from any Run's model. To predict tip vortex cavitation, both adaptive grid refinement and turbulence model are important, more than the cavitation model. The Schnerr-Sauer model appears to be doing pretty well together with LES in this application. Here is a summary of this lecture. An accurate simulation of flows with phase change, like direct numerical simulation, DNS, is a great challenge, requiring adaptive grid refinement to resolve the temperature gradient at the liquid-gas interface. Such simulations are performed within the research community, providing valuable data for a better understanding of physics and for the development of Run's models. For the simulation of engineering flows with phase change, usually Run's models are used. Heat transfer and phase change at gas-liquid interfaces are modeled using heat and mass transfer coefficients based on empirical data, usually valid for a small range of flow types. Simulation of cavitation is an example of using the mixture model and volume of fluid approach to predict the phase change in zones where pressure drops below saturation level for given temperature. In spite of crude modeling of cavitation phase change, good results can be obtained if the grid is locally refined and an appropriate turbulence model is used.